In this video, we're going to use properties of exponents to simplify expressions that contain rational exponents. So if we're going to use the properties of rational exponents, we probably should review what those properties of rational exponents look like. So we're going to go through, there are 5 main ones, and just discuss in general what these mean so that we can utilize them as we move forward and simplify expressions that contain rational exponents. The first property is when we are multiplying two terms that have a common base. So what I'd like you to notice here is that you have a common base, and then each one has a different power, or they might have the same power, but the important part is that they have a common base. So you can see here this is a to the power of m times a to the power of n. And when you have common bases and a multiplication symbol in between, you are simply adding together the exponents. And that's because we're pretending we have a situation like x squared times x to the third. Well, we have 2x's being multiplied and then 3x's being multiplied with that for a total of 5. Now for this particular unit, we're going to be working with rational exponents. We're going to take this same idea of, x squared times x to the third, but we're going to apply it to rational exponents. So say we had a common base to the power of 1/2 times a common base to the power of 3/2. It works the same way as when we had integers. We add the two exponents together, so this would become x to the power of, that would become 4/2 because we have a common denominator, so we add the numerators, and that would simplify to x squared. So anytime we have common bases that are being multiplied, we simply add our exponents together. The second property we're going to look at here is called powers raised to powers. And when we take a look at this one, hopefully what you're noticing is that we have a number inside of parentheses, or a base inside of parentheses, and we have a power that is then raised to another power. So notice it's different. There aren't multiple bases that are common. In this case, we have a to the power of m then raised to the power of n. So that would be something like x squared raised to the power of 3. And because of what the definition of cubed means, this would be something like x squared times x squared times x squared. This would become x to the power of 6. So we don't add this time if we have powers raised to powers. We multiply when we have powers raised to powers. So anytime you see a power raised to another power, you're going to be multiplying. Now what's kind of cool about this is if you had something like a to the power of, 2 times b to the power of 1/2, and you had these both raised to the power of 4, the powers to powers rule, because both of these items inside of the parentheses are being multiplied together, both of these would get multiplied by 4. The powers to powers rule would apply to both. So this would become a to the power of 2 times 4, b to the power of 1/2 times 4. So that would ultimately become a to the power of 8, and b to the power of, that would become 4/2, so that would become 2. The other cool thing about this property is that it also applies when we have some sort of fraction. So say we have, a to the power of 1/4 over b to the power of 1/2, and say that this is raised to the power of 3. Again, here, because of how powers to powers work, each one of these powers would get multiplied by 3. So it would become a to the power of 3/4 over b to the power of 3/2. So we have situations now where we add our exponents together. We're looking for common bases that then we add the powers. And then here we have powers raised to powers, which is where we multiply our exponents together. So property number 3 deals with dividing. So what you're going to notice here is that when we're dividing two terms that have the same base, what we can do is we can actually subtract their exponents. And there are two ways that we can approach this. One, we can always aim to have our answer go into our numerator. So say we had a to the power of 3/4 over a to the power of 5/4. Now in the example here you can see we have m minus n. In this case the order matters. So you could turn this into a to the power of 3/4 minus 5/4, which would become a to the power of negative 2/4, which simplifies to a to the power of negative 1/2. So that is an option that you can take. The other option is that you can subtract them and leave them where there were more a's to begin with, or where the bigger exponent was. So for this particular example, we can see that 5/4 is the bigger number because 5/4 is about 1 1/4, where 3/4 is less than 1. So what you can also do is take 5/4 minus 3/4, that becomes 2/4, and you leave it where the larger exponent is. So this would become a to the power of 2/4 in the denominator, and it would simplify to 1 over a to the power of positive 1/2. And we'll talk on the next slide about why this can be true. But when you have two terms, one in the numerator, one in the denominator, that have a common base, that's the important piece. If you're dividing those two terms, you can simply subtract their exponents, and you can either take the approach of numerator exponent minus denominator exponent, and then leave that whole answer in the numerator, or you can subtract the smaller number from the larger to keep that exponent positive, and then leave them where the larger exponent was to begin with. So in this case, that happened to be the denominator. Now property number 4 deals with the property of 0, and this works every time a is not equal to 0. That's just because a equals 0 is a different unique case. But anytime we have a number to the power of 0, that is going to equal 1. So we could have, x, b, c, all in parentheses to the power of 0. That entire statement will equal 1. We can have 32,768, all raised to the power of 0. That will equal 1. So anytime we have a base raised to a power of 0, it is going to equal 1. And that's because if we apply that division property we just talked about, so say we had, a to the power of 4 over a to the power of 4. Well, we just learned that if we're dividing with common bases, that is going to become a to the power of m minus n, or the numerator minus the denominator, so 4 minus 4, which is a to the power of 0. Now, in this particular case, we know that we have something divided by itself. We know that any number, it doesn't matter what. So say we had 4 over 4, that equals 1. 6 over 6, that equals 1. 7 over 7, that equals 1. If we have a number divided by itself, it always equals 1, which is why a to the power of 0 always results in 1. The final property we're going to look at here deals with negative exponents. And what's really unique about negative exponents is that we can write any term with a negative exponent into its positive exponent equivalent. So we can always change negative exponents. Now, unfortunately, this doesn't work if we have a negative base. We can't change a negative base to be positive, but we can change a negative exponent to be positive by flipping it to its reciprocal. So here you can see we took a to the power of negative m, and in order to flip it to its positive, all we had to do was turn it into a fraction and flip it to its reciprocal. So we move that negative exponent term into the denominator in this case, and it becomes a positive exponent. So to give you a couple of more real-life examples, say we had 5 to the power of negative 1/7. In order to turn this into something with a positive exponent, we flip it to its reciprocal, which in this case becomes 5 to the power of positive 1/7 in the denominator, and then we have to put something in the numerator, so we have a 1. We might also see something like 1 over 3 to the power of negative 1/2. Again, we have a negative exponent. If we want to turn this into its positive exponent equivalent, we flip it to its reciprocal by moving it to the other side of the fraction. So in this case, this would become 3 to the power of positive 1/2. You can put it over 1, but anything over 1 just becomes itself. So here you can see how we can rewrite any expression that contains a negative exponent into a positive exponent by changing it to its reciprocal. Now, this works for everything except for when a is equal to 0, because again, a is equal to 0 is a unique case. So here we're going to use the properties of rational exponents to simplify the following. And our goal is to have no negative exponents at the very end of the problem. So let's start with this first example. What I notice here is I have common bases. So I know that when I have common bases, I'm probably going to be using an adding or subtracting of exponents. Because these two things are being multiplied, I know that I'm going to add the two exponents together. So this is going to become 2 to the power of 1/4 plus 1/2. So what we're going to need to do now is we're going to need to add 1/4 and 1/2 together. So let's just kind of do that off on the side. We have 1/4 plus 1/2. Well, I know that in order to add those together, I need to get common denominators. So I need to multiply this one by 2 in both numerator and denominator. So that becomes 1/4 plus 2/4, which added together becomes 3/4. So my final answer here would become 2 to the power of 3/4. Then from here, if we look at the second example, this one I can see that I have common bases. Now, what looks a little deceiving here is we can see that that 3 in the numerator currently doesn't have an exponent, but remember that if there's not an exponent there, that is kind of just an implied 1 because it's 3 to the power of 1. So because we're dividing with a common base of 3, what we can do is we can take 3 to the power of the numerator exponent 1 minus the denominator exponent of 1/4. So again, we're in a situation where we're going to have to get common denominators. So I'm going to turn 1 into a fraction of 1/1. And we have 1/1 minus 1/4. Well, I can turn 1/1 into fourths by multiplying both numerator and denominator by 4s. So I get 4/4 minus 1/4. So that becomes 3/4. So my final answer here is 3 to the power of 3/4. So I found common bases in numerator and denominator, which means I can subtract their exponents. Now this next one here I can see is a case where I have powers raised to powers because I have a set of parentheses and a power raised on the outside. So remember, when we have powers raised to powers, we're going to take each of these and we're going to multiply them by that power on the outside, which is 3. So this becomes 5 to the power of 1/3 times, I'm going to do 3/1, then times 7 to the power of 1/4 times 3/1. So this becomes 5 to the power of 3/3 times 7 to the power of 3/4, which can then simplify to 5 to the power of 1, or just 5, 7 to the power of 3/4. Now, as tempting as it might be to combine these together further, you can't because they do not have a common base. 5 is one base, 7 is another base. They are not common. They are not the same. So as a result, we cannot combine these further. Now, if I asked you to multiply, you could figure out what 5 was and what 7 to the power of 3/4 was and multiply those together. But in this case, I'm just simplifying it, so I don't actually need to multiply out to find those decimal values in this situation. Okay, moving on. So here in this next one, what we can do is we have a situation where we're going to multiply both numerator and denominator by that 7 because we have a power, we have powers on the inside raised to a power on the outside. So this becomes 20 to the power of 7/2 because we're multiplying this by 7. And then the denominator becomes 5 to the power of 7/2. Now, in this case, it might look like we're done, but what's really unique about if we have the same power, so say we have 7/2 and 7/2. If we have the same power, what we can actually do is we can group the 20 and the 5 together. In this case, because it's division, we can actually divide them. If it was multiplication, we could actually multiply them. So if you have a common exponent here, what you can do is you can move that exponent to the outside because they're in common, and you can actually perform the operation, which in this case is 20/5. So this ultimately becomes 4 to the power of 7 over 2. Now in the previous examples, I didn't actually figure out what any of these expressions involving exponents actually equaled, but that's because I couldn't take, in this case, the 4th root of 2 very easily, or the 4th root of 3 very easily, or even the 4th root of 7 very easily. But in this case, I know that I can take the square root of 2. So I can separate this out and think about the fact that this can really be represented as, remember, you can split it up into 4 to the power of 1/2 to the power of 7, or you know that that denominator is a root, so you can really split this up into the square root of 4 to the power of 7. And so then from here, we can actually square root the 4 and actually work on figuring out what this actually equals. So if we take the square root of 4, we know the square root of 4 is 2. And so now we're looking at 2 to the power of 7. 2 to the power of 7 is 2, 4, 8, 16, 32, 64, 128. So this expression here in problem number 4 can actually be simplified all the way down to 128. So now let's move over and take a look at number 5. So here again, we can add in a 1 here because anything without a power has an implied 1. And then we have another powers to powers, so we can multiply this power here of -4 to both the 1 and the 1/3. So we end up with 5 to the power of 1 times -4, which is -4. And then we end up with 8 to the power of 1/3 times -4, which is -4 over 3. Now, we know that we can rewrite anything that contains negative exponents to have positive exponents by flipping it to its reciprocal, which means if we move the 8 to the power of -4/3 up and the 5 to the power of -4 down, we're actually going to end up with positive exponents. So here we have 8 to the power of 4 over 3 over 5 to the power of 4. Now again, in this case, these are exponents that we can actually evaluate. We know that we can take the 3rd root of 8. So we can rewrite this as the 3rd root of 8 and then put the 4 on the outside, still as a power. And then 5 to the power of 4 is also something that we can evaluate. So here, if we think about what to the power of 3 gives us 8, we know that that numerator is really 2 to the power of 4. And then you have 5 to the power of 4 in your denominator, which is 5 times 5 times 5 times 5. So that's going to give us 625. And then here, 2 to the power of 4 is 2, 4, 8, 16. So here we end up with 16 over 625. So when we can evaluate a fractional exponent or a rational exponent, we should. Now finally, this last example over here, we again have a powers to powers situation, so we can multiply those out. We know that this becomes 16 to the power of 2/8 over 16 to the power of 2/4. Now it's best practice to simplify out those exponents to make them a little easier to work with. So this is going to become 16 to the power of 1/4. And then 16 to the power of 1/2. So then these actually turn into roots that we can evaluate. So I'm going to move it down a little bit to give myself a little more space. So here we have a root of 4 in the top. So we have the 4th root of 16 in the top. And then you can keep that 1 on the outside if you want, but because it's a numerator of 1, we don't have to include it. And then we have the square root of 16 in the bottom. Now this we're looking for what number to the power of 4 gives us 16. In this case, that is 2. And then down here we have what number squared gives us 16. So that's down here. And that gives us 4. And then from here, all we have to do is simplify. We find that our answer is equal to 1/2.